All right. Tooling, feed speed, depth of cut. Anything else? Tool geometry. Anything else? CAM software. Anything else? The operator. Anything else? Climb versus conventional milling. Anything else? Yeah. Coolant, whether it's on or off, what kind of coolant it is. Yep. The operator. Somebody said that, but go. Good. All right. So there's a lot of things that impact our ability to make the part, right? One of the things that impacts our ability to make the part. What's the key word in computer-controlled machining? There's 3 words, right? Go. Computer's one of the key words. What else? Controlled. We have an idea what control means, right? Like when somebody tells you to do something and you do it, that means you're controlled by that person, at least for that instance, right? When the computer tells the machine to do something, what does the machine do? It does exactly what it was told to do, regardless of what the programmer intended, right? Do you believe that? Computers do exactly what you tell them to do, regardless of what you meant to tell them to do. Anybody ever experienced this before? Yeah. Do you have a good example? No? No. Do you have a good example? Using a laser cutter. Okay, so it's sort of like CNC machining. It's a kind of CNC machining. Oh, what did you light on fire?
I was short cutting stuff for high school or helping out.
Mm-hmm.
Cutting paper out in the
Yeah. Too much heat in the paper at the one location catches the paper on fire. We have had to replace components of our laser cutter because people have caught shit on fire. Next to our laser cutter, there is a carbon dioxide fire extinguisher, which can be used to put those fires out. In fact, if you don't spray too long, you can use it to put out several small fires. I personally have never had a fire in the laser cutter that I couldn't put out by blowing on it, but other people have. So yeah, laser cutters, you catch stuff on fire because it did exactly what you told it to do, right? Yeah. So I have a pretty good experience. And it's actually kind of funny because I owned the machine tool. I owned the tool that was in the machine tool. I guess I owned the workpiece that was in the machine tool, but I really intended to sell it to somebody else. And I had just spent most of a day setting up the fixture. And it was about a $2,000 tool. And I was all ready to go. I've been testing it, checking stuff out. And my partner says, "Don't you want to dry run that?" And so a dry run in a CNC machine tool is where you haven't run the program, but you've adjusted the work offset so that it will run above where the part is. And I said, "Nah, it'll be okay." Press the cycle start button. Now, I'll give you all some advice. I thought I knew what was going to happen. You should never press the green cycle start button on the machine in order to find out what's going to happen. Whenever you press that green button, you should at least believe that you know what's going to happen. And so what's the immediate reaction when you hear a noise that's not the right noise after you press the green button? Right? And so I was here. Let's go. All right, so the controller, I got... Sweet. I was glued to the ceiling. So, all right, so here's my, too bad there's no red chalk. Here's my e-stop. Here's power on, power off, cycle start, feed hold. We got the stuff. You guys have seen the Haas controller, right? This was a Haas machine. And so I said, nah, it'll be all right. Cycle start to turn around. Hear the noise. E-stop. Yeah, we lost the $2,000 tool. The fixture was thrown across the machine. Did I mention that it took most of a day to set up the fixture? The part was okay. And any guesses what happened? Anybody want to guess? Yeah. No. Program was perfect. Program was perfect. Spindle turned on. That was one of the things that I knew was wrong. Heard the spindle start. Any other guesses? When you're running the program, so in your screen here, the lines of code of the program will sort of scroll by. Has anybody noticed that yet? The lines of code of the program scroll by. The line that is highlighted is the line that's going to happen now. It was not at the beginning of the program. Because I had run my graphical simulation. You guys have run the graphical simulation on the controllers? I ran my graphical simulation. But it was a long process. I didn't want to watch the whole thing. I ran it until I decided that, yes, this is the right program, and yes, it's going to work as I intended. And I pressed feed hold, or I don't know what I pressed. What I didn't press was reset, which is right above that cycle start button. And it's actually one of the reasons that all of the machines in our machine shop here have a little sticker right next to that cycle start button that says press reset before cycle start. Because if I had pressed reset, it would have gone to the top of the program. And so what it did when it started in the middle of the program was it had to, in order to do this line of code, it had to be in the position that it would have been in at the end of that line of code. So it immediately started the spindle and moved the tool to that position, which wasn't where it needed to be for when I was starting. So yeah, computers do exactly what you tell them to every time you tell them to do that, which is kind of an issue with computer-controlled machining. You'd wish they would do what you intended for them to do. What we're going to talk about today, we're going to focus on, is that step of transitioning from what you thought you told the computer to tell it to do and bringing it over to what the machine tool is going to do because that's what you actually told the computer to tell it to do. And so that process of going from the computer, from our, they call it, in a spree, they call it a cutter location file, and you'll never look at a cutter location file. But that's the data file that's in the background of all of your spree files that tells the spree exactly what order to do the different steps, where to go, when to move from here to here. And they've got then translators. Would you believe that there are many manufacturers of CNC machine tools, not just Hobbs? Yeah. Many manufacturers of CNC machine tools. Also many manufacturers of CNC controllers. Now the code that runs, the stuff that scrolls by on the screen here, that's called G code or G&M code or NC code. First, what's the NC come from? Numeric control, right? So that's our NC. Anybody know what G comes from? Because these are names that get used interchangeably. I might use 2 or 3 of these in the same sentence, in fact, when I'm talking about it. Anybody know what the G comes from? Some of you have done this, right? Anybody ever written G code? So what's the G come from, Gus? You didn't look it up. Could you guess? Yes.
Like, I don't know what it stands for, but they're just like movement commands.
Most of the G commands are movement commands.
Right.
I would agree. Most of the G commands have to do with movement. So it turns out that every line of code in NC code, G&M code, or G code starts with the letter G or the letter M. Or the letter N. But if it is the letter N, it means that it's a line number, and the controller skips over that and doesn't read it. So the controller ignores any lines that start with N. The other exception would be you might have one that starts with parentheses, open parentheses, close parentheses. This is a comment. Right. And so you put comments in there. Well, why do you put comments in the code? Yes. It helps you break up the sections of code into different sections, yes. Why do we always, who's, any CS majors in the room? Really? Anybody had a computer science class in their life? Right, I'm guessing all the hands go up here, right? Is that not required in high schools? No? But most of you guys had one, right? So when you're doing any kind of programming, what are the comments for? Yes? It certainly helps the next person understand what the code does. It helps you yourself remember what that line of code was supposed to do. Maybe you haven't looked at this program for a year. It helps you remember what it is you're doing. Years ago, I actually, at one point in my life, I had the job title Senior Software Engineer. And one of the things that I did as part of that job was write code. But the best part of that job was there were people who wrote code who worked for me. Because it's totally cooler to have people work for you and do the work than it is to do the work if you have a management mindset. At any rate, it's pretty frustrating when somebody else writes the code. And then you have to come edit the code or maintain the code later. And you have no clue what it was they were thinking when they wrote that line of code. It got to a point, so years and years ago, people would pay coders, software people, by lines of code. So you write 1,500 lines of code, maybe you get paid $1 a line, you get $1,500 to write 1,500 lines of code. That's kind of like hiring a carpenter, telling them you want to build a house over there somewhere and saying, I'll just pay you for all the nails you use, right? But we used to pay software engineers like that. And it got to the point where I said, I don't want to pay them per line of code. I would like to pay them per line of comment. Because the comments were more important to me when I was coming back in later. Okay, so you put comments in your code, G&M Code. This, again, takes us from the CAM software to the machine tool controller. Esprit holds the information in what's called a cutter location file that's always the same no matter what. And then they have a thing called a post processor, which translates the cutter location file. 10 minutes. It's been 10 minutes since I touched the computer. They're afraid that you're going to sneak up here during lecture and change your grade while I'm logged into the computer. So therefore, the podium computers time out after 10 minutes to make sure that you can't sneak on when my account's logged in. Yeah. Can you log back into the computer there? Because I'm not even logged in. He is. So that I can go to the step that I was just about to do, which was going to be show stuff on the computer. Where are we? Yeah, put comments in your code. In class and in WPI, we will not encourage you to write G&M code by hand. Yes?
Does the G actually stand for something like NC, control, so does the,
No, I honestly, like Gus, I didn't bother to look it up. I just infer that we call it G code because most of the lines of code start with a G. Let me open up. If I put this in presentation mode, it shouldn't time out. You asked, yeah. Maybe it means go. Maybe it means go. We could, you know, if I make it up and then I say it in a believable enough tone of voice, it could become true. You guys know this, right? If you say something over and over again enough times, it becomes true. Times it. Okay, quick little aside. When I took this job, the main reason I took this job was to learn if I enjoyed teaching. Because I had never been a teacher before, never been an instructor before. I wanted to know if I liked teaching. And I decided I did like it. Although the night before my very first ME1800 lecture, I did not sleep. How about you guys? Did you guys sleep the night before your first lecture? Man. Because it was your first ME1800 lecture. No, I had given lectures for other people in their classes before, and I had no trouble sleeping those nights. But when it was my class, I actually didn't sleep the night before my first lecture. Anyway, so I like teaching. So I decided I want to be good at teaching. If you like something, you should become good at it. So I started studying the writings that people write about how to teach. I started studying how people teach. Yeah, I didn't like anything that they said. It just, I don't know. They were just trying to publish papers to get journal, or I don't know. But then I says, but if I understand how people learn, maybe I could be a good teacher. So I started studying learning, which was kind of cool. And the people who write about learning, I think, do a better job of understanding what's going on than the people who write about teaching. But I really wanted to be good at it. And so from learning, I actually transitioned to marketing. So and there was other business reasons that I wanted to learn about marketing. I sort of started studying marketing while I was studying learning and realized they were really the same thing. So what do the marketer want you to do? They want you to know about their offer, right? Right? So I want you to know about my knowledge when I'm teaching you. And I really came to the conclusion that I cannot teach anyone anything. But perhaps I could inspire them to want to learn it and provide them with resources that enable them to learn it. So, all right, so we're logged back into the computer. Took the job to do teaching. I like teaching. End of the story. From marketing, I totally started researching brainwashing. Which is where you get to the thing. If you say something over and over again, it becomes true, regardless of the facts that back it up. And if you observe your life and the things around you, you'll note that most marketing is intended to be brainwashing. Why do politicians put yard signs up? Does it tell you about their values? It's name recognition, right? It's so that when you get to the voting booth, and we vote in Worcester in just a few weeks here, when you get to the voting booth, when you see their name on the ballot and you remember their name, you're like, oh, that's the guy I like, and you vote for them. It's all brainwashing. So my intent in this class is to brainwash you into wanting to know about manufacturing. And then, I mean, if you want to know, you'll figure it out. Right, let me, I can go to a particular slide, right? We talked about PBs and machining. Let's just talk about the process of going. So, let me switch the right projector to the PC. All right. So what's the process that we're going to take if we want to go? So what's the art again? Yeah. The art is the design. The art is the definition of the part that we want. Whose job is the art? No, it's not the manufacturer. Whose job is the art? The designer, right? Whoever the designer is, they're responsible for the art. We're the manufacturer. We're responsible for the part. Now, our part's going to be based on the art. So what do we have to do if we want to take a part from art to part? Based on what we know so far, what do you want to do? What are the steps you want to take? What do I have to decide? Right? So here's my art. You guys recognize this part? You've all made this part, or should have. Almost all of you have made this part by now. If you haven't made it by the end of the day today, we're going to give you one because we're not setting that lab up again. But I don't think there's anybody that'll be in that condition unless they were sick all week. So we know this part. This is the art. The art defines it to us as the manufacturing engineers. What's the first thing I have to do when I see the art if I'm a manufacturing engineer? Yes. So I have to look at the specifications. I have to decide if I understand what the art means. Okay. I do have to do that. It actually, at this moment, it's not horrible to have a conversation with the customer and make sure and discuss the specifications, the art, and make sure that they interpret the art the same way that you do, especially if it's a new customer or something like that. So it's not horrible. Yeah, what do I have to do once we understand the art?
You have to make sure it's actually machinable.
Sometimes the customer will ask you to make stuff that's unreasonable. Sometimes you may have to negotiate with the customer to change their design to make it more reasonable. I hate to say impossible. Because most things, if I throw enough money at them, I could probably make them. but you do want it to be machinable, and you want it to be machinable in a cost-effective manner. And you sort of take care of that when you're understanding the art. So once we understand the art, it's a machinable piece. We understand what the customer wants. We know that we have the capability to make what the customer wants. What do we have to do first in our process? Yes. Do we have to decide how? First thing we want to do is decide how, right? And so you guys cut this part in 2 setups, right? Is there another way we could cut the part? Yes. Who said yes? So your 2 setups, I believe you put it in where if we're looking down here, right? Let me adjust this slightly for all of you watching on YouTube at home now. All right. So our first operation, the spindle was above this orientation of the workpiece, or of the part, right? And so we cut, I don't remember the order that we went, but I'm guessing that we cut a contour around it like this. We drilled and tapped the holes, and we did a surfacing operation to remove the material in the V. Is that what happened? Maybe not that same order, but that's what happened, right? So we did that. Then we flipped it over, clamped it on this part, and we did a thing where that big base mill spiraled around the part. Was that cool when it threw the chips at the window? Yeah. That's why we do that the first day. Because we totally want you guys to see cool stuff on the first day. It was a term. So, I mean, when you're at the machine, what do you have to do first? You have to put the workpiece in the machine, fixture it, right? Then you have to tell the machine where the workpiece is. Maybe you load the code before you do that step, but that's pretty at the beginning. There was a few terms where we taught the class in the order in which you do the operations at the machine. And so we spent like the first 2 weeks teaching people how to set up the machine, but never turned on the spindle. And 2 weeks into the class, somebody in the classroom says, "Hey, professor, when do we use the machines that cut metal?" And I realized my mistake. We need to cut metal on the first day. So you understand we're using the machine that cuts metal to do the setup operations. They thought we were just learning how to measure stuff. First 2 weeks. Okay, so what if I was going to cut it in 3 operations, what would I do instead? And we could cut it in 57 operations, but 3 is the next obvious choice from 2. How would I do it? Somebody? Yeah, Andy.
So you take it and you do, so you've got that tapered cylinder kind of thing. So you could do one side of that, coming down on that thing from one side, then you could do the other side, and then you could do the face with the Y on it.
Uh-huh. I never thought of doing it that way, but yes, you could. That's not what I would do. Anybody else? Anybody? Yeah. Oh, you could do that too. The really the most obvious thing to do, I think, if you've cut a few parts. So if we're looking down at the machine here, and that's the top of the vice jaws, does that make sense to you? If I'm looking down at the, so I am the spindle, I'm looking at the top of the vice jaws, and so we've got our little parallels here that we put our workpiece on, and then we put our workpiece here. So we put our workpiece there, we could do a contouring operation that makes a V in the end of it, right? Then we could stand it up so that it's got this side pointed up, make the contour around it and drill and tap the holes, but then we don't have to do that surfacing operation to go down inside the V. Does that make sense? So what do we notice about, well, I mean, you can see it here in the picture. Tell me about that surface roughness. What do you notice about the surface there immediately? It's not, right? The drawing shows a smooth surface. This is clearly not a smooth surface, right? What causes the scallops that we see on that surface? Let's just look at the profile. So if we're looking at the side of that part, Right? If that's one side of the Y, and now you know why I'm an engineer and not an artist. But if we're looking at the front view of the part, what causes this roughness here? Because you can see we've got roughness in that direction along the part, right? I mean, that's maybe not even roughness, maybe that's waviness. What causes that feature? Physics.
I was going to say, wouldn't that be because of the, like, that side, like as you,
Yep, you've got it. So if this would be the top now, we're feeding in that direction. As the tool goes around the part, it also feeds down. And it goes around the part and it feeds down. It goes around the part and it feeds down, right? So the radius at the bottom of that scallop is equal to the radius of the cutting insert that was on that tool. And the spacing between the two scallops is equal to the feed in, well, whatever units, inches per revolution, where the revolution is the tool going around the part, not the spindle spinning a revolution. And it's the same on a turned part. So we do a turned part. So our turned part spinning this way, our tool is here, right? Feed is that direction. So as the tool feeds over, it doesn't make a smooth surface there. It actually makes little scallops. Across there. And so the distance here is the feed in inches per revolution, in length per revolution. It doesn't matter if it's inches, millimeters, kilometers, although it'd be a really small number if it was kilometers probably, right? So you get that. You actually, with a little bit of math, you can calculate this distance too. Right? Because that's just the depth. So you get the chord length across the chord there from your circle, because you can imagine that it's a circle. You get a chord that goes across there. It's the depth from the chord to the edge of the circle. And so mathematically, you can calculate that distance too. We do that sometimes to choose what feed rate we want to use based on how smooth we want that surface to be. So if I want this to be smoother, how do I adjust my parameters? If I want the side of that Y block to be smoother, how do I adjust my parameter? Yeah. Slow the feed down would do it. What else could I do? Yep. As typically what we would say, so that's roughly the same as slowing the feed down, because we almost always talk about feed and turning as feed per revolution. And what you wanted to do is keep the per minute feed the same, but spin faster, which is roughly the same as slowing the feed down. What else can we do? Use a smaller tool. Actually, if we have a larger radius, it will make those less deep for the same feed. So the other thing they do is they actually put another feature on the tool called a wiper. And it's actually, so the features. These are the things that the part has. So this part has what features, right? It's got these tapped holes. It's got 3 tapped holes on it. It's got this V feature. It's got the, I don't know, what do we call this shape? The parabolic. This was originally, when it was designed, it was actually tapered in 2 directions, just to make it harder. But it's got the tapped holes. It's got that Y shape, right? Those are the features on the part. So identify the features. We decide how we're going to cut it. So in this case, and we decide how we're going to cut it and how we're going to fixture it, how we're going to hold on to it once it gets in the machine. And so in this case, I've got the example of holding it sideways in the part, make the V. That's what our tool path looked like. So we actually came in here, removed this material, and then we did a contouring pass. So we did a pocketing operation and a contouring operation there. So at this point, to make this feature, we've got to have a toolpath, right? So we've got to get tools. We've got to get feed speed, depth of cut. We've got to figure out what's the approach move. How's the tool going to get to the part? How's the tool going to leave the part? We've got to tell the CAM software all those things. We select our process variables there. When you do this, so we get everything all figured out, then we bring it to the machine, right? Then we bring it to the machine. Then we have to load the tools in the machine, set the tool offsets, fixture the workpiece, locate the workpiece. Then we can run the machining operation. This one is key, right? That's part of Shine from our lean lecture. Clean up. If the part has sharp edges on it, one, try to design your processes so that you don't leave sharp edges on the part. If the part has sharp edges on it, when you take it out of the machine is the time to deal with that because you're already holding the part in your hand. If you fill up a box full of parts with sharp edges, then you have some, and here's what you would do in manufacturing. You fill up the box with a part with sharp edges, and then you realize, we can't ship the part with sharp edges. So you hire a temp to come in and take all the parts out of the box to deburr the edges, take the sharpness off the edges. Just do it when you have it in your hand. You might have to do post-part inspection. We'll talk about that at length next week. And then ship it to the customer. So it's not that much to do, right? People, especially students, graduate students, not so much the graduate students, advisors of the graduate students. They'll sometimes want to talk about why it takes their graduate students so long to get the help that they're expecting in the machine shops. And especially when they find out it was just a 2-minute cut time. It's not so much the 2 minutes that the tool spends cutting the part in the machine. It's the 3 weeks that it took you to get to those 2 minutes. That's what takes so long, right? So if we get better at it, if we practice, we get better at it. But this is our flow in art to part. It would be really cool for me if there was a clock on that side of the room. So I would know how much time I had left when I'm doing this. Plenty of time. Perfect. All right. So we figured out how we're going to hold it. We've figured out what tool we're going to use, right? Now we have to put that in the CAM software. And you guys are going to, if you haven't started doing this yet, you're going to do this at length for the next, what do we got, 6 weeks left in the class? For the next 4 or 5 weeks, you're going to do a bunch of this. And you're going to get plenty of practice doing this. So we got our CAM software open. We're going to make a pocketing operation right here. So what's a pocket on a milled part? Gus? When you remove material from the inside of something. Does this look like a pocket? This is what we call in machinist speak an open pocket. We can in fact have an open pocket that's open on all 4 sides. This one's actually closed on, so it's closed here, it's closed along that arc, it's closed here, and it's only open on one side, but this is what we call an open pocket. Now we're using a pocketing operation because it allows us to control the tool path in specific ways. We could also have simply done a contouring operation here, right? So what's a contouring operation? This is in our stuff, right? What's a contouring operation? It's Max, right? No, Sam? Yeah. There's a Max, though. He sat here on the first day. Is Max here? He's back. I must have spit on him the first day. He's sitting further back now. Sam. So a contouring or a side milling operation is when the tool moves along the edge of the part here like this, right? So we could have just done a contouring operation. And so part of the problem with just doing a contouring operation is the tool would have come along here, it would have buried itself in the workpiece, it would have come out. And in fact, if we did a contouring operation with that tool in this shape, because I've seen people try it, so we start with our workpiece here. The tool path for that contouring operation would come over here. It would go in like this. It would come out like this. It would go off like that. That'll make the shape, right? The tool diameter to scale is roughly like that, which means when it's down here in the bottom, so what would happen there is you'd make a little V-shaped piece. As the tool went in and came back out, there'd be a little V-shaped piece. When the tool got over here and it's just barely connected, that little V-shaped piece would do that across the machine. It's pretty safe. It's an enclosed machine, right? The mini mills actually don't have tops. You should know that. Anybody notice the coolant spray out of the top yet? It happens. Sometimes hot chips come out and they go down the back of your shirt. It's uncomfortable. This much I can guarantee. That's pretty rare in the mini mill because that mini mill doesn't have enough power to really make the chips hot. The MDC, though, one of the machines in the next room, that also has an open top, and I've gotten hot chips from that one. Andy.
So when's it okay to like?
When is it okay to do that?
Like, as opposed to like you could make multiple passes and not have that happen, but like is it? You're saying that it would be fine for the tool though to do that? It just wouldn't necessarily.
If this tool could handle that with the right feed speed depth of cut. So you'll notice on the tool charts, it says for full slotting, reduce the feed rate by 20 or 30% or something like that. It may also reduce the depth when you do full slotting. And so if you select the right feed speed and depth of cut, this tool could handle that operation. What's really bad, though, is that moment when the part flies off, the little piece flies off, it may suck itself back into the tool, which may chip the flutes on the tool. So doing operations like that tends to shorten the tool life. So at WPI, your question was, when is it okay to do that? I would say don't do it. Turn the whole thing into chips, which is why in our toolpath over here, we turn the whole thing into chips. We weren't going to collect that little piece and use it again for something else, right? So sometimes it's not practical to turn the rest of the material into chips, and you do want to do a slotting operation that cuts something out. When you do that, you've got to hold the piece that's being cut out and hold the bulk material so that nothing moves when it does that cutoff. That's all you have to do. All right, so we can do that, but we're going to do an open pocketing operation. We've got to tell it what tool we want, right? We had to select the tool. We had to decide what tool we wanted. We're going to tell it feed, right? And somewhere there's speed. I will get to speed. Oh, speed, right up the top. Feed speed. We'll get to depth of cut. It's on a different tab. You'll notice here in our pocketing operation, we've got general, we've got strategy, we've got pocket, we've got rough, we've got links. There's a lot of stuff to fill in on the page, right? Every one of those things is a process variable. Every one of those things is something you get to choose. If we went back, no, I want to go the other way. Back over here, we said wall finish no and floor finish no. If we had checked yes on those two items, there would have been two more tabs. One for the wall finish and one for the floor finish. This is a lot of process variables. Feed speed, depth of cut. Okay, here's our step over. Is that axial or radial depth? Anybody remember? Anybody remember? It'll be important to know that on the quiz.
I'm going to say radial.
Okay, he's going to say radial. Honestly, I never remember. When I have to know, I go look it up. You guys do know that the quizzes are open notes, open book, right? And in fact, we encourage you to talk to each other. I try very hard to make it impossible for you to cheat. So I encourage you to talk to each other. Now, you're cheating yourself. I forget your name. Josh. Josh is really smart. Do you guys notice that? And I forgot your name. And I can't quite read it. Evan. Evan's kind of a slacker. Do you guys notice that? So Evan, it's okay for you to ask Josh what the answers to the quiz are. And Josh, it's okay for you to tell Evan what the answers to the quiz are. Evan, you're not going to learn nothing that way. And Josh, you're not really doing him a favor. Unless you explain to him why that's the answer. In which case, Evan might learn, and you might be doing him a favor, and you're going to understand it better because you've explained it to somebody else now. Don't be wrong when you do that, Josh, by the way. And Evan, you should know that Josh might be wrong. Hell, I might be wrong. I thought I was once, but I was mistaken. Okay, feet speed, depth of cut. Have you guys seen this equation yet? Surface speed times 4 divided by tool diameter. What's 4 equal to? 12 divided by pi. Why is there a 12 and a pi in the equation?
12 inches in a foot, and then pi is for you want to calculate the circumference of the tool.
12 inches in a foot. We always give tool diameters and part diameters in inches. We always give surface speed in feet, mostly just to confuse you guys. Well, it's so that the machinists can confuse the young engineers. You know what we call you guys when you get to the field? When you're practicing engineers in the field? Yeah. Kids with CAD. Because you're really good at drawing shit and have no idea how it's going to get made. And as soon as you bring that drawing to the guy in the machine shop, he knows that you're a kid with CAD. Because he knows that you've drawn stuff that the tool does. You said make sure it's machinable, right? The tool ain't going to reach that location in that geometry. Oh, you guys use SolidWorks? Most of you have taken the SolidWorks class, intro to drawing class here and stuff like that. You've played around with CAD software. Man, that fillet button is cool, huh? And the blend button. Oh, let's blend these two surfaces together. Sometimes I advise MQPs. Once I was advising an MQP with 12 students on the team. They were broken up into subgroups. So this group was taking care of this part of the MQP. This group was taking care of this part of the MQP. One of the guys was taking care of the manufacturing part of the MQP. And by the way, especially if there's multiple advisors and you're doing an MQP, the group should have a meeting to talk about whatever they're going to talk to the advisors about before the advisors get there. Okay? But one of the kids puts up his CAD model for it was a front steering knuckle for a car that they were building. He puts up his CAD model for this knuckle. And Wayne stands up, feet apart. Dude, how are you going to make that? Wayne was not one of the advisors. Wayne was one of the students on the project. And Wayne is now is a good friend. He actually owns a machine shop not too far away from here. So Wayne figured out how to make stuff. So yeah, pi over 4. Yeah, to try to keep you kids with CAD from understanding what's going on. Do you have to memorize this equation? Why? Because the quizzes are open book, open notes, right? I don't think I would look this equation up ever. Why wouldn't you look this equation up even if you didn't know what it was and you had to do the math? Because you understand first principles, right? And so I have this debate with colleagues, and they say, you should make them memorize the equations. And I say, why would you ever memorize the equation? They're engineers. They should be able to figure out the equation. Let them know that an equation exists. That helps them along the way. Google. By the way, getting back to you should have gotten a 4 out of 4 on the first Sunday quiz. There was not a single question on that quiz that if you highlighted the question text, right-clicked and said search Google, within 3 links you wouldn't have found the answer. Not a single question. Or the equation that gets you the answer. You wouldn't necessarily get the answer, but you would have found the equation, like this one. In fact, that Google might have brought you to this slide for the surface speed one. Okay, go through those things. So yeah, all right, power things. We talked about, so we got our depth this way, stuff there, incremental depth. That's how far down we come, right? I think that's axial. And I think radial is step over. Do not quote me. Whatever I wrote in the reading thing, that's correct because when I wrote that, I looked it up. Incremental depth, step over. Here's another pocket. This pocket is enclosed in a part. You know, ME1800 used to make this part. It was the base for the Stirling engine. Thing is, when we made this part, we didn't make the Stirling engine parts of the Stirling engine. We bought those and we bolted them on the base. So what we were really doing at that time was making a holder for a Stirling engine. We thought it was much more cool now to actually make a Stirling engine. So there's step over, the percent diameter, all those things. All right, so you guys got a pen, pencil? You should write this down. In fact, if you learn anything at WPI, this is the thing. The thing I'm about to say right now. If you learn anything at WPI, this is the thing that you should remember. And I will say it in verse. Engineering's math. Engineering's math, just a bunch of word problems. Cancel the units. You can always derive the equation if you know what the units are. And you know what the input variables are. Right? You can always do that. If you remember anything else at WPI, remember that you can always cancel the units. But there's a lot of stuff to fill in. If we go back here, there's a lot of stuff to fill in here, right? There's a lot of parameters. I got another haiku for you. Goes along with this one. Feed speed, depth of cut. Guessing, not recommended. Carbide explosion. Which I think is my best haiku ever. How do we avoid guessing? Yes? That's sort of guess and check. And sometimes we do that. Sometimes we do guess and check. How do we avoid guessing altogether? Yes? You could do the math. We don't always know all the parameters to put into the math, though. So if we don't know the parameters, we don't want to guess and check. So we can't do all the math. If we're looking up the so what we do sometimes is we have to look up the numbers in order to do the math, right? So how do we avoid guessing? If someone else has done the research, go look it up. Use reference material to avoid guessing. One of the things that we'll use in the class is the Machinery's Handbook. So I've given you some reading so far out of the book that I'm trying to write. I get about a chapter a year written. So it might be a while before this comes out of the draft form. But in next week's reading will be from my latest chapter. Some of the words are yet to be typed. So if you find typos, it's because I was typing the word a few minutes before you were reading it. So this one won't have seen a copy editor before you see it. Please feel free to let me know. I don't care. If it's something that you can't understand because the typo is so bad, let me know. What else we got here? You know, if you go through this, post-process is the next thing. It'll show you that in your code, like program name, you can put it in the CAM software. It shows up in the code. This is very similar to the first part of the first lesson in the CAM exercise. So I think this is a little bit redundant here. I don't know what that circle is supposed to be circling. Probably this here. All right, let's go. Yeah. I will try to only test you on things that we've talked about in class for the most part. I will guarantee that I won't test you on anything that you can't figure out the answer to. Because you guys all got accepted to WPI. So you're all smart. So if there's some question on the quiz, on the final exam, probably not on the final exam, but some question, and you say, but he didn't teach us that. What do you remember from today's lecture? I cannot teach you anything. I can only inspire you to want to learn it and provide you with resources. And if all else fails, Google. And if you ask me a really stupid question and I'm in a bad mood when I get the question, I may respond with a link to let me Google that for you. But it's got to be a pretty bad question, and I've got to be in a pretty bad mood before that happens. And if you haven't checked out, let me Google that for you. You should check it out because it's really funny. Okay. Oh, and the audio with the YouTube Live was not connected yesterday. I have now downloaded the audio from Echo, merged it with the YouTube video, and I will repost the YouTube Live video with that in there. It was rendering when I came over here. So I was, yeah, go ahead.
Post the quiz on Friday.
No, I usually post the quiz before the week starts. I just haven't finished making new quiz questions yet. It'll be up today.
Okay, cool.
Go for it. Should we turn this off before we, especially since it's like close up on you right now?
Oh, that's scary. Sorry.
That's right. I didn't have your face in it. It's like your shoulder.